materials. Okay. We'll talk about various materials that are used for the fabrication of cutting tools and why we are using a particular type of material. So we'll see the merits and demerits of all those cutting tool materials. So I think CR can record this class.
Yes, sir.
So my voice may not be that clear. You have to just bear with that. I'm suffering from cold. So we are talking about the cutting tool materials. So what are the essential properties of a cutting tool material? Okay. So first thing is hot hardness. We all know that cutting tool material should have a higher hardness compared to the workpiece material. Then only cutting will take place. But that alone is not sufficient. So at elevated temperatures, okay, or during cutting process, some temperature will be generated. So at the elevated temperature, when you are increasing the heat of the temperature, hardness of any material will come down. Okay. So even after increasing the temperature, okay, to a certain level, that means around the heat, suppose let us say there is some 200°C is generated during cutting process. So at 200°C, now whether our cutting tool material will be hard enough to cut the material from the workpiece. So that is hot hardness. Okay, and is even after heating also, it should have the hardness. So the ability of a metal to retain its hardness at elevated temperatures, that is hot hardness. This is one important property of the cutting tool material. Now next is toughness. So what is toughness? Resistance of a material to breakage, chipping, or cracking under impact or stress. So toughness is opposite to brittleness. Okay, to understand it, we can say like that. So toughness means what is toughness? I mean, in your words, you can say what is toughness. Here, exact definition is not given. Here they are saying it is resistance of a material to breakage, chipping, and cracking under impact stress. This is indirect way of putting the toughness definition. What is the simple definition of toughness?
Resistance of the material.
Resistance to, yeah, resistance to what?
To oppose the deformation.
Yes, toughness is resistance to deformation. Okay, or the ability to absorb the energy for a given material. So if the tool material is tough, okay, so it will not break, instead it will, okay, absorb the energy, okay, and it will not deform. Understand? If the toughness is high, and it will not break also at the same time. Understand? If it is brittle, it will break because it can absorb the energy, so it will not break. Okay, up to certain limit if the toughness is high. Understand? So it will oppose the deformation. That is also important. Okay, tool should not deform during cutting process. If it is deforming, then obviously you will not get the required finish, etc. So it should not deform. So for that, it should have good toughness and wear resistance. The ability of a metal to resist the gradual wearing wearing away caused by abrasion and friction. So wearing means a gradual removal of the material. So that should be very less. That means the resistance should be high, wearing should be less. Okay, because as you know, the tool is in contact with the workpiece. Okay, there is a continuous relative motion is there. So definitely there will be some sort of a wear for the cutting tool, but it should be very minimum. Okay. Now why tool will wear actually? We are saying that workpiece material is having less hardness compared to tool material. Then also the tool is wearing out gradually. Okay, very in the very minute quantities it will wear out. Okay. So of course we will see the reasons in another. But here, as of now, you can understand that there will be some inclusions in the workpiece material. Okay. So suppose if you are saying that is mild steel workpiece, it will not be pure mild steel. Inside that there will be some okay impurities like carbides, sulfides, okay, silica, silicon, okay, etc. Very minor quantities of those will also be present, and whenever the tool is encountering those particles, so then the tool will wear. Now here there is this hardness, okay, ranges for various tool materials is given. So we'll talk about these tool materials, but okay, you understand that these are the hardness ranges. HSS tool 83 to 86. So cast alloys 82 to 84. Carbides, tungsten carbide 1800 to 2400. Titanium carbide up to 3200. Ceramics 2000 to 3000. CBN is cubic boron nitride. It is about 4000 to 5000. And diamond about 7000 to 8000. Okay, these are the hardness ranges. So based on the application means a type of workpiece material and the process parameters, we have to choose the appropriate cutting tool material. Now hardness versus temperature, we all know that. So here you can see as the temperature is increasing, hardness is coming down for any material. Okay. And if you see carbon tool steels, okay, so their hardness is coming down rapidly, okay, with the temperature. And then you can see other things. If you see ceramics, okay, as the temperature is increasing, the hardness is coming down anyhow, but rate is okay, not very high. So ceramics can withstand higher temperatures without losing their shape. So followed by carbides, okay, like that. High speed steel is also losing its hardness at elevated temperatures, but it is better than carbon tool steels. Okay, like that. So with the temperature, hardness is decreasing, and ceramics having the better hardness compared to other materials. So here you can see we will generally add some okay other materials into the existing tool material. Like suppose if you are taking on tungsten, okay, we'll not use only pure tungsten. We'll add some other material into it to enhance its properties. Okay, like that. If you are using carbide, it may not be pure carbide. You'll include some other material. Now you can see what are the properties you will get when you are including a particular material. So if you are including tungsten into the tool material, it will increase the hardness. Hard carbides will form. It improves the abrasion resistance. Okay, if you are including tungsten carbide will form. So that will be very hard and its resistance will increase. Okay, abrasive, this wear resistance will increase. Abrasion means one kind of wear only. So it also increases the hardness. Now molybdenum, again it increases hardness. Hard carbides will form. This will also again improve the abrasion resistance. Chromium, depth hardenability during heat treatment, improving abrasion resistance and corrosion resistance. So this is main thing is corrosion here. So if you are including chromium, so corrosion resistance will improve. Corrosion resistance is also one required property for the tool material, but it is not the very important parameter. Okay. Vanadium, it combines with carbon for wear resistance, retards grain growth for better toughness. So if you are adding vanadium, it will decrease the grain growth. That means you will have fine grains. So fine grains means better toughness. Okay. If you have larger grains, then it will become brittle and it will break. Cobalt, it acts as a solvent matrix and it increases the wear resistance. So cobalt will be generally used with the tungsten, okay, tungsten carbide and cobalt combination. So it will act as a binder. Carbon, obviously it forms carbides. So it is a hardening element. So hardness will increase when you are increasing the carbon content. So now coming to the type of tool materials one by one. So first we will see the carbon steels. So high carbon steels are used as cutting tool materials. So carbon range is like this, 0.6 to 1.5%. So it is a steel, but high carbon steel. Now small percentage of silicon, manganese, chromium and vanadium are used to help refine grind size and increase tool hardness. We have seen, okay, by including some of these chromium, vanadium, okay, etc. But silicon, manganese is also given here. We have not discussed those separately, but silicon again will increase the hardness, etc. So we are including them, okay, for increasing the toughness and hardness. So one advantage is easily shaped and sharpened. You can easily, okay, make the required geometry for the cutting tool because okay, machining them, machining carbon steels is not very difficult. Okay, so that is the advantage. And greater resistance to abrasive wear. So this is also one advantage. Abrasive wear will be less. And do not have sufficient hot hardness, 200 degrees Celsius, for cutting at high speeds. So hot hardness is very less. We have seen that in diagram also. So that is one major disadvantage. So you cannot operate, you cannot use carbon steels at high speeds. Okay. So at 200 degrees Celsius itself, its hardness is very less. Now widely used for files, saw blades, chisels, taps, broaches, and reamers. These are also cutting tools. Okay, file is a, we will not say it is a single point cutting tool. Okay, it is a kind of tool. It is not exactly cutting tool. We will say file, saw blades, okay, chisels. These are all tools used to remove the material. So they can be made with these carbon steels. You might have already seen in workshop. Have you gone through workshop? I wonder. Have you visited the workshop or have you been to workshop? Maybe some of you, because
Yes, sir.
yeah. So there you might have seen these files. Okay, you might have done filing for fitting operations. So those files, okay, they are carbon steel files only. Chisels also you might have seen in carpentry, etc. Now speeds range is about 5 meter per minute. Okay, very low speeds. Carbon steels can be used at very low speeds. At high speeds, it is losing its hardness. So that is about carbon steels. Now the next type is high speed steels. Okay, short form is HSS. So this is very famous cutting tool material. So this is one of the tool materials developed for cutting tool purpose in the initial stages. Okay, that's why it is used. Name is given as high speed steel. At those okay, at that point of time, so this cutting tool material was used at higher speeds. That was the high speed at that point of time. But now things have changed. Now this is low speed only. But okay, name has remained same. So high speed steel. High speed tool steel differs from plain high carbon steel in the addition of alloying elements to harden and strengthen the steel and make it more heat resistance. So it can okay, can be operated up to 600 degrees Celsius. Hot hardness is high. Okay. So alloying elements include manganese, chromium, tungsten, vanadium, molybdenum, cobalt, and niobium. So here there are two series okay, in HSS. One is one is called M series. So here you will have 10% of molybdenum with chromium, vanadium, tungsten, and cobalt as remaining materials. And of course, the rest will be ferrous. Represents tool steels of the molybdenum type. So this is molybdenum type. HSS M series means molybdenum type. So 10% of molybdenum. Another is T series. So here you have tungsten content is high. 18% tungsten, 4% chromium, 1% vanadium, and cobalt as alloying elements represent those of the tungsten type. So this is T series because of tungsten. Even though the chemical representation is W, it just starts with a T, so it is T series. The tool geometry and mechanics of chip formation are complex, such as helical twist drills, reamers, gear cutters, farm tools, broaches, etc. So here HSS tool can be used for the complex cutting tool materials. Now what is complex cutting tool material? Single point turning tool is a simple geometry we can understand. Okay. But if you are talking about a drill bit, twist drill, so you will have flutes cut on the drill bit. Okay. Helix shape is there. So that is a complex shape. Okay. So for such kind of cutting tools, we can use HSS material. Okay. Reamer, Then gear cutter, that is also one kind of tool. Okay, if you are talking about any farm tools, farming operation on lathe machine, so there you can use the HSS material. Now brittle tools like carbides, ceramics, etc. are not suitable under shock loading. So shock loading means force is varying. So whenever there is varying force, so brittle materials cannot withstand, they will break. Okay, even though they are hard, if they are brittle, they will break. So HSS advantage is mainly it is tough. Okay, toughness is high, very high compared to many other tool materials. Not many other, I will say, it will have the best toughness among these. Okay, tool materials. So it can be used for shock loading cases. Now, when will you encounter these shock loading? And suppose step turning. Okay, if you are doing some eccentric turning. Okay, then in those cases you will have this shock loading. The small scale industries cannot afford costlier tools. That is also one of the reasons for using HSS. HSS is cheap compared to other tool materials like carbides, okay, or any other. CBN diamond is anyhow, okay, very costly. The older low-powered small machine tools cannot accept high speed and feed. So if you are dealing with old machines, so they can be used at very low speeds and feeds only. So then you cannot use the carbide tools, etc. They will break at low speeds. Okay, so they should be used at high speeds only. So here, so then you can use a HSS tool. Tool is to be used a number of times by resharpening. This is also one great advantage. So once okay, you lose the cutting edge or the shape, you can regrind the tool, then reuse it. So this advantage is there. It is not there with other tools like carbides, etc. It is very difficult. Now, another type of tool material is cast cobalt alloys. So here, a typical composition for this class of tool material is 45% cobalt, 21% tungsten, and 2% carbon, which gives a hot hardness of 750 degrees Celsius. So here its hot hardness is better. Now, cast cobalt alloys provide high abrasion resistance and are thus useful for cutting scaly materials. So because so here you have high amount of cobalt. Okay, so cobalt means it is resistance, abrasion resistance is high. Okay, corrosion resistance is also high. So once the abrasion resistance is high, so you can cut the scaly materials. Now, what is scaly material? So on the surface of the material, some scaling has formed due to oxidation. So those kind of materials can be cut. They are not as tough as HSS and are sensitive for interrupted cutting operations. So toughness is less compared to HSS. So they cannot be used for interrupted cutting operations. So they may fail. When applying cast cobalt alloy tools, their brittleness should be kept in mind and sufficient support should be provided. So they are brittle. So that is a problem. So When you are dealing with the brittle material, you should not operate at low speeds, and there should not be any fluctuation in the cutting forces, etc. Okay. So if you are operating at high speed, a high amount of force will come onto the cutting tool. So then it will break. Now speed range is about 45 to 60 meter per minute. Now next is carbides. So this is also known as cemented or sintered carbide. So here you can see high hardness, about 1000 degrees Celsius, up to 1000 degrees Celsius will have good hardness. High elastic modulus. So elastic modulus is high means what does it mean? So it will not break easily. Okay. Elasticity is more. Now high thermal conductivity, high abrasive resistance, and high chemical stability. So these are the properties of these carbides. Okay. So most carbide tools are either straight tungsten carbide. So carbide tool means it is not any carbide, generally tungsten carbide, or multi-carbides of tungsten titanium. That means tungsten carbide, titanium carbide combination, or tungsten titanium and tantalum carbides. So depending upon the work material. So you can use this in the range of 150 to 250 meter per minute speeds. So these are some of the typical carbide inserts used for single point cutting tool here. So there are many shapes like a triangle and rhombus shape, square shape, etc. You can also see some chip breakers are also inbuilt. So okay, along the edges you observe carefully. Okay, it is not flat on the top surface. Understood. So the design is given for chip breaking purpose. It is not any fancy design there. Okay. So the holes in the inserts are standardized for interchangeability. So this insert, there will be one tool holder, and you will take this insert and attach this insert to the tool holder. So that central hole will be used for the clamping purpose. Okay. So these are carbide inserts. Now once let us say we have used one cutting edge, let us say this one. Okay. So once this is used, okay, let us say it has worn out after some time. Now you can use another side as the cutting edge, this side. Understand? So 2 times you can use it, this particular tool. Understand? Because other side anyhow, because of cutting here, this side will also be damaged here. So here 2 times, and if you turn this upside down, that means this top surface will go to the bottom and bottom surface will come to the top. Now again you can use it for 2 more times. So like that you can use these inserts.
Sir, then the triangle shape can be used thrice, no sir?
It can be used here, yes, thrice. Thrice means total 6 times on either side. This rhombus shape only, this disadvantage is there. Okay. Otherwise, if you see square, it can be used 4 times. Understand? One side 4 and another side 4. But it is also required sometimes. Rama shape means you will have very sharp okay, cutting what is that, a lip angle. So if you want to remove very thin material, okay, this is advantages. Now methods of attaching inserts to tool holders. So this anyhow we have seen earlier. One way is you can directly brace this cutting insert into the tool holder. It will be permanent. And so that is one way. Generally, we won't prefer it. Okay, that is that kind of method is preferred only for ceramic inserts, maybe, or CBM diamond, not for carbide inserts. So generally, clamping is used. Okay. So this is green one is a tool holder. Red portion is a tool insert. Okay, there will be seating here. I mean, seating means one. Okay, geometry is cut on the holder so that the insert will come and sit there. So then you will clamp it. One is you can use clamping like this, or otherwise there will be a through hole here. Okay, at the center, and you will use one nut, and you can fix it. And there are different ways of clamping the insert. One is this kind, another, then bracing is also there. Yeah, here this is another method. This is what. So you'll put the insert here, and then using this nut, you will fix it. Okay. So this is through bracing. Now insert strength. So you can see if it is circular inserts are also there, but very rarely we'll use them. Okay. So so square type. Square means not exactly 90 degree, need not be. Okay. 100-degree angle. Okay, that is one type of insert. 90 degree, perfect square. 80 degree, 60 degree, that is a triangle. 55 degree, okay, and 35 degree. These are some of the standard okay, cutting tool shapes, cutting tool insert shapes. Now here if you see these, increased chipping and breaking in this order. Just so here you can see relative edge strength and tendency for chipping and breaking of inserts with various shapes. So here chipping and breaking, if you go in this direction, it is increasing. Understand? So that means here it is strong. Here it is okay, little bit compared to this, its strength is less. So this is obvious, isn't it? When the tool is becoming thin, okay, its chipping and breaking capacity will increase. More chipping and breakage chances will also be more. But the tool is sharp, that is the advantage. And with less amount of force, you can remove the material. That is the advantage. So same thing, increasing edge strength. So here you will have better edge strength, second best like that. Negative with land and cone. So there will be some landing is also provided sometimes for the cutting tool. Landing means, so generally this is the cutting tool shape. So for some of the cutting tools, they will be like this. Here you are providing some okay negative rake, very small okay length you are providing. After that it is anyhow positive rake only. Okay, so because you want to increase the strength of this tip. Okay, so this kind of landing is also provided on some of the cutting tools. So hone is nothing but you are rounding off this cutting edge to some extent. It will not be exactly sharp. You are providing some curvature. So if you are doing that, you will have better edge strength. So anyhow, I am talking about this is a positive rake. Okay, if it is a negative rake and you are providing landing and hone, so all three combinations, then strength is very high, edge strength. Negative rake and land, okay, little bit less strength. Negative and hone, okay, little bit less. So this is the order. Negative and sharp. So finally, positive with hone and positive with sharp edge will have the lowest strength. But these are also required, okay, because sharpness is the ultimate thing we want. For cutting purpose, we should have sharp cutting tool. So just because to increase the strength, we cannot go for these other tools. But if you okay want to cut the very high strength material, then you have to put okay, you have to use these kind of a negative rake angle. Okay, depending upon the application, you have to choose. All are required for okay, different applications. Now another type of a cutting tool material is coated carbide inserts. So necessity why we need coated carbide inserts. New alloys and engineered materials which have high strength and toughness, and these materials are generally abrasive and chemically reactive with tool materials. So now recently we are we inventing different new materials like nickel based alloys, magnesium based alloys, titanium alloys. So there are many alloys are coming up. So if you want to cut them, you need very high strength and high toughness also should be there for the cutting tools. And one more problem is they will be chemically reactive with the cutting tool material. Why they are chemically reactive means, so generally cutting tool material itself will have tungsten, titanium, etc. But your workpiece is having now titanium, let us say. We are considering titanium carbide cutting tool and workpiece is a titanium alloy. Now obviously there will be chemical affinity. Titanium is present in both the tool and the workpiece, but maybe different quantities. That is one problem actually. So at elevated temperature, diffusion will take place. Okay. So from high density to low density, material will transfer. So that will not work. Okay, if you have the same material in the workpiece and the tool. So that's why you have to use this coated carbide inserts. Now, need for improving the performance in machining common engineering materials has led to important developments in coated tools. So for existing materials also, if not the advanced materials, existing materials, if you want to get okay good surface finish, etc., you can use coated carbide inserts. The thickness of these coatings is in the order of 2 to 10 microns. So coating is very thin. Okay, very thin layer of coating will be given on the cutting insert. Inside material maybe some carbide insert will be there. On top of that, you will coat some other material like titanium carbide. Okay, we'll see what are the general coating materials also. Now you can use these coated insert, carbide inserts in the speed ranges of about 200 to 250 meter per minute. Now, what is the role of coatings, or why we are coating the insert? I mean, by coating, what are you achieving? Reduction of abrasion, adhesion, and diffusion wear. Okay, if you are coating with suitable material, let us say, for example, titanium carbide. So titanium carbide is okay. Abrasive resistance is high. It's okay. It may not be adhesive to the workpiece material, depending upon the workpiece material that you are cutting, and diffusion wear will also be less. Okay. Now reduction of friction and built-up edge formation. To avoid these, we are coating with the different materials. Don't think that we are coating only titanium carbide, and if you are coating titanium carbide, you cannot machine titanium alloys. You have to machine some other. Okay. So reduction of friction and built-up edge formation. So friction will reduce by coatings. Okay. Some of the coatings will reduce the friction. So chip will smoothly slide over this rake surface. So built-up edge formation will also be reduced. So that is one advantage when you are coating. Now heat resistance and a reduction of thermal cracking and plastic deformation. So these coatings will have greater heat resistance. So thermal cracking can be avoided and plastic deformation can also be avoided. Now what is this thermal cracking? So during cutting, temperature is increasing. So after once you stop the machining process, or whenever you are pausing the machining process, so obviously the tool will be cooled off. Then the cracking may take place. Okay. Then plastic deformation, when the temperature is high, material will become soft and plastic deformation may take place. But when you are coating with heat resistance material, so you can avoid this cracking and plastic deformation. So improve the surface quality. Okay, if the friction is less by coating, okay, and you can remove the material with less force, then obviously surface finish will be better. So this is one major thing you have to observe. Coated tools don't perform efficiently at low cutting speeds. Okay, because coated materials are generally brittle in nature. So if you are using at low speeds, again they will break. Okay, at high speeds only you consider the coated tools. Coating materials, titanium nitride is one coating material that is gold in color. Its properties include low friction coefficient, high hardness, resistance to high temperature. Titanium carbide, gray in color, high flank wear resistance. Okay, in machining abrasive materials and good adhesion to the substrate. So it will easily adhere to the substrate because titanium carbide and insert is also carbide insert. So there will be good bonding between these. Okay. And because it is carbide, it can withstand abrasion for abrasion. Okay. So flank wear takes place due to abrasion mainly abrasion. Okay. There are other forms of wear also. We'll study them later. Ceramics, they are black in color, high chemical inertness. We all know that ceramics are chemically inert. Okay, that's why from the olden days itself, we say we store these chemicals or at least pickles, etc., in ceramic okay, pots and vessels. So chemical inertness is there. Low thermal conductivity. This is also well known. High thermal stability. Okay, so heat resistance to flank and crater wear also. Flank wear means high abrasion. So crater wear generally due to adhesion. So adhesion will also be less. However, ceramic coatings bond weakly to the substrate. This is the problem. So their bonding with the substrate is weak. So this is another combination of this carbon and nitrogen combination. So normally appears as the intermediate layer of 2 or 3 phase coatings. So sometimes what you do is you will coat 2-3 different materials on the same insert, one after the other, layer by layer. 2-3 layers will also be used sometimes. So in those cases, it is used as intermediate coating. Okay. So because at the bottom you will use titanium carbide. So intermediate you can use titanium carbon nitride, and on top you can use titanium nitride. So for example, so the bonding will be good in that way. Acts as a neutral layer, helping the other coatings layers to bond into a sandwich-like structure. So these, to some extent, we have seen in the previous slides. Again, you can see various cutting tool inserts and their shapes. Okay, triangular, rhombus, square, circular, okay, etc. Triple coated tools. So that is carbide insert. Now you are coating with 3 different layers. You can see this is a carbide substrate. So that is the carbide substrate means carbide insert, whatever you have taken. Now you are coating titanium carbide as first layer because the bonding will be good. Okay, carbide. Then you are using aluminum oxide as the second layer here. Okay, the combinations will vary depending upon the requirement. This is one example. Aluminum oxide as the second layer. Now titanium nitride is used at the top. Okay. So this aluminum oxide is bonding well with the titanium carbide and as well as titanium nitride. Okay. So then you are using aluminum oxide. We have also seen now titanium carbonitride is used as the sandwich material. That is also another combination. Okay. So this is one example given here. So here the second case you can see tungsten carbide is the material. Then you are coating titanium carbide as the first layer. Okay, aluminum oxide as the second layer, titanium nitride at the top. So same thing. First layer should bond well with the substrate. Intermediate layer should bond well and compatible with both the layers. Outer layer should resist wear and have low thermal conductivity. So for this reason, we are going for this triple coating. high speed continuous cutting to titanium carbide, aluminum oxide or alumina. Okay, so these triple coated tools are used for these. Heavy duty continuous cutting titanium carbide, alumina. So these are the combinations. Understand? If you want to operate at high speed, continuous cutting speed, use titanium carbide, alumina. So heavy duty continuous cutting, you can use titanium carbide, alumina, titanium nitride. Light interrupted cutting, you can use this titanium carbide, okay, these combinations. So depending upon the application, you choose the combination of materials. Now next is ceramics. Ceramics are non-metallic materials produced by sintering process. So sintering means you take the material in the powder form. This is nothing but a powder metallurgy. Take the material in powder form, compact it, then sinter that. That means you will heat it below its melting temperature, so the material will bond together. So ceramic inserts are prepared through this powder metallurgy method. Main constituent is alumina with an approximate 10% oxides of magnesium, titanium, and chromium. So mainly in ceramic tools, you will use alumina, and you will mix remaining materials of magnesium oxide, titanium, and chromium oxides. Small quantities of those will be included. Why? Because aluminum is cheap, but we need some of the good properties of magnesium, titanium, and chromium. We are including them in small quantities. Extremely high resistance to abrasive wear and cratering. So because ceramic itself is very hard, and of course it is brittle also at the same time. So it wear resistance is high. Okay. Extremely high hot hardness. So hot hardness you can see up to 1400 degrees Celsius. So these tools can work. And a low thermal conductivity makes it possible to use speeds up to 300 meter per minute. So here speed has increased further. So these are some of the ceramic inserts. So you can see here mainly they are white or black in color. Okay. So white means alumina in general. So here some kind of carbides. Carbide means carbide insert is different. Okay. It is a tungsten carbide, etc. So here like silicon carbide, boron carbide. Okay, they are ceramic materials. So they are black in color. Okay. Mainly alumina is used because it is widely available and it is suitable for the cutting tool material. Alumina ceramics, advantages, disadvantages. Very high hardness. Okay. Hot hardness is also high. Chemical stability will be there for any ceramic in general. Thermal conductivity is less. These are the properties of alumina, that's it. Okay. High melting point, high abrasive resistance. Now, shortcomings, poor toughness. For any ceramic material, toughness is less. Poor tensile strength, yes, that means the material is very brittle. Okay, poor traverse rupture strength. Traverse rupture strength means so material is like this. If you apply force vertical to it, it will break easily. So that is traverse rupture strength is less. So those are the disadvantages. Okay. Okay, for today, let us stop here. We have ceramides and okay, CBN and diamond. So we'll see them in the next class.
Excuse me, sir, I have a doubt. Sir, when these coatings are not, I mean, like they will get damaged at lower speeds, no, sir. Then how are they being able to manage at higher speeds without damaging?
See, at lower speeds, what happens is friction will be high. Okay, adhesion tendency will also be high. Okay, so at lower speeds, we also understand that the formation of built-up edge chances are high. So workpiece material will be sticking to the cutting tool surface. So what will happen is the coated layer will come off, okay, with this workpiece material. Understand? That is one main disadvantage at lower speeds. And at lower speeds, brittle material will break easily. Okay. At higher speeds, it will not break. That means it should be uniform. Speed, you cannot use okay, brittle materials at low speeds. They will easily break because high force will be coming on them. At higher speeds, the force coming onto them is less, but you have to use very less feed and speed. Combination is important. Low speed, feed, and high speed. For that combination, ceramic tools will work better. Is it
Yes,
clear?
sir. Understood. Understood, sir.
Yeah. That's all for today. Anything else to discuss? I hope all of you are preparing for this minor. Okay, that's all for today. Have a good day.
Thank you, sir.
Thank you, sir.
Thank you, sir.